Hey YouTube, the next few episodes are going to be amazing. We're going to be learning so much and this will be extremely useful in many of your own projects. But before I begin, I would like to say a massive thank you to all my subscribers because we just hit 215 subscribers and I am super excited, so thank you. This video was a result of an amazing suggestion from Grant Christie, which has been an amazing journey of learning for me. So what are we actually doing? Over the next 2 or 3 parts, I'll be creating an aiming system in Unity for our stealth game with dynamic IK that we are coding from scratch, which will allow us to reposition our arms in order to suit any situation, while maintaining the animation and allowing a wide range of variety in our weapon holding. The videos that you see in the background are a result of 2 parts of work, which is a basic IK system, but this is not the end result. We'll still work on holding a gun and the body leaning over to reach an extreme position. This system was built from scratch and it has no Unity's built-in IK system, so don't worry, I will have a massive explanation which will go into depth about how the algorithm works in this episode. I know in the video you can only see the IK system being implemented in the arms, but this algorithm called FABRIK can be easily used to rig a full body model and implement torso rotation and more fun stuff like that. So we started quite easy with the aiming so you can understand the basics of FABRIK, and soon we will be adding more powerful IK to this game. The first part of the IK setup, we will just be working on setting up the first parts of the IK, which will be the left and right arm, and allowing these joints to be able to reach a target in no specific natural way. Then in the next episode, we will implement constraints and root movement, which will allow for realistic movement in the arm and leaning the body in order for it to reach a further position. Then we will wrap a real arm mesh around the joints so the actual arms can move. This is a video like none other on YouTube, and it took a lot of effort to create alongside with my school, so if you leave a like it would motivate me a lot. We have a lot of work ahead of us and we're going to learn something amazing. If you would like to learn more about FABRIK, then I've put some links down below in the description, but I will try and explain it to the best of my ability. Remember, if you have a suggestion, leave it down below and I will be sure to add it as soon as I can. If you haven't already, make sure to subscribe to keep up with the original content, and thanks again to Grant Christie for the amazing suggestion. And without any further ado, let's get right into the tutorial. Alright guys, I'm going to get right into the video. So before we begin actually coding our FABRIK algorithm onto our player, I am going to show you a quick video on how FABRIK works and how we are going to be implementing it into this game. And it's not going to be in Unity, so I'll see you in Photoshop. Okay guys, so I'm going to explain the FABRIK algorithm before I actually start coding it. So I have an example set up here, so I'm just going to explain the example, then I'm going to teach you how the algorithm works. It's actually very interesting and most of you can use it in your own games. Okay, so we have 3 green dots here, so what do they represent? They are your joints, okay? So this is a basic example of an arm, okay? So let's just pretend this is an arm, and don't mind my handwriting. This is your arm. Imagine that the root is your shoulder of your actual arm. So just reach out on your arm and just look at all the different joints. Your first joint is your shoulder, okay? That's your root. The lower arm is your elbow, the middle joint of your arm, okay? And your hand joint, this one over here, is your wrist. Okay, so these are the 3 joints that we're going to be manipulating during our inverse kinematics algorithm in order for us to be able to move the hand around in a natural way. So how this is going to work is we're going to be using an algorithm called FABRIK. So its shortened name is FABRIK. So let me just write this out for you. FABRIK. That's really tiny. There we go, FABRIK. So what does this stand for? Okay, what does this FABRIK stand for? FABRIK stands for forwards and backwards reaching inverse kinematics. Okay, this is the full name. Okay, and how we're going to be doing this is through these 5 steps. I have modified the algorithm slightly to make it more useful for our purpose, which is in the end going to be aiming our hand to be able to hold a gun in a natural way. So forwards and backwards reaching inverse kinematics is the full name. So how can I show you what this is? So the first step, as it shows on our little list here, is calculate values. Okay, what does it mean by calculating values? Calculating values is finding the distance between each joint, okay? So the distance between the root and the lower arm might be 3. Okay, let's just save that, and we'll save that as a private variable at the very start, and we won't modify that at all. Okay, and then we're going to get the distance from the lower arm and the hand, and let's say the distance is 4. Okay, we're going to save that variable as well. So what is this actually useful for? Okay, now I want you guys to just reach out your arm. Okay, we're going to be using it for a second, and just imagine, okay, that you can't move your body. Okay, you can only move your arm. You can do that, right? When you move your arm to try and grab something, okay, without leaning over and trying to grab it, okay, try to grab something. As you can see, your arm actually doesn't like modify its actual length between the joints. What actually happens is your arm rotates in a way that it can grab an object. Okay, if something is closer, your arm will be more tucked in and bent towards your body, and you can pick it up. If something is further away, you'll be reaching towards it, and you may be able to grab it or you may not. That's the type of natural movement that we're going to achieve in the next 3 or 2 episodes, okay? We're gonna be achieving more than that, actually, more than what most inverse kinematic algorithms on YouTube can do. So what our algorithm can actually do is make our body lean over to reach something if it's way too far away. Okay, so that will happen naturally. Everything that happens will be natural. And then we're going to add constraints, so our body can only move a certain distance, because if you try to lean over, you can see that you can only lean a maximum distance. You can't lean like all the way to the other side of the room. You can only lean a maximum distance, so we're going to have constraints, and we're going to be implementing most of this algorithm into our game, except I've modified it and made it a lot simpler. If you want the full, more complicated version to this algorithm, I put a paper down in the description. Just download that and read it. The constraints are extremely complicated, and I haven't been able to figure out yet, personally. So we're not using Unity's inbuilt inverse kinematic system. We're going to be coding this from scratch. Everything is going to be done by us. Okay, so first we've calculated the values. So we can just cross this out. We're done. We're done that, okay? And also calculating values is just setting some temporary positions. Alright, so these green dots are actually just temporary, not temporary points. These are going to be like little cubes in our scene that we will modify, and then we'll get an arm mesh that we'll make in Blender and wrap the mesh around the joints. So we're not going to be applying the algorithm directly to the mesh. That'll be way too jittery and just not look good. Okay, so we've got these initial values. How let's just erase some stuff. We don't need. I'm on the wrong layer, so let me just go in and just go to target, and let me get rid of all of this. We don't need it right now. I just want to explain to you how this all would work. Oh god, that doesn't look good. And let me just explain this. We just need all of this. Okay, so now let's imagine that our target is over here. Okay, that's our target over there. And how do we rotate, or not rotate, move the joints? Because FABRIK is a vector-based solving algorithm which does not rotate joints, instead moves temporary positions and then rotates them after it's moved the positions. Okay, so if we've got this temporary position, not temporary, this end effector here, okay, an end effector is the target that we're trying to reach. If this is our target, how do we move these joints in order to be over there? Okay, so let me explain. So the first thing that we will do is we will set a temporary position at the target. Okay, let's just imagine that pink thing was in the center. Okay, so this temporary pink dot represents the hand joint. So this hand joint is no longer here. Okay, so we can go into the target layer and just rub this out. Okay, uh, just need to find this. Here we go. And one second, I just want to make this easier for me and you. Just gonna go in, merge layers. Alright, there we go. So let's imagine that we move the hand joint over here. The hand joint is now over here. So what we're going to do is now this joint is connected like this. But this white circle is a lot closer to this lower joint than the hand originally was. So the hand, let's say, was up to here. I'm just speaking metaphorically. Okay, let's just say the hand was over here, and this had a distance of 4. Okay, and this new point where the hand is now only has a distance of 2. Okay, so how do we make this distance 4 again? Okay, is the whole problem. So what we're going to do is we're going to find a direction between the new hand joint and the lower joint. Okay, so this is the direction vector. Okay, so that's the way that the lower joint is. And we're going to normalize that direction and times it by 4. So we're getting the vector and timesing it by our original distance. And what this will essentially do is it will get a direction, right, in the direction of the lower joint, except when you multiply that by 4, you may get a point around here. So what we do now is we have a new lower joint point as well. So let me just get rid of this and get a new circle object. Let me just increase this and we'll start visualizing like this. So now let's imagine that our lower joint has been moved over here. Okay, so now we've maintained the position of the distance between the lower and the hand joint. It's 4 now. Okay, so we no longer only have a distance of 2, we have a distance of 4 between the hand and the lower joint. Okay, now we need to manage the distance between the lower joint and the root joint. Okay, so we can see now that the distance between the lower joint and the root joint may only be around 1 because it's a lot closer than it was before. How do we make sure that the point maintains a distance of 3? All we do is we do the same process as before. Let's say we go from the new lower joint all the way, we get the direction, right? So the direction is down there, multiply by 3, which was our original distance, and we make it a point around here. This is our new root point. So now we have a type of joint like this. Okay, going about here, we have another joint over here and another joint over there, and our hand is exactly at the target. We have reached the target, right? No, we have not reached the target yet because we need to do the next part. So this was the backward step. I put the steps wrong, but that's fine. We need to go backwards first always in this algorithm, and now we do the next part, which should be the forwards. Okay, so the problem with this now is that the root was originally over here. Since the root was here, we can't actually move the root joint because the root joint always has to stay the same. So because the root was originally here, what we do is we repeat the process except in the opposite direction. So we set the root back to its original point where it started, which was here. So we set this new root position back to its original root, and then now we can see that the distance between the lower and the upper joint have again changed to around maybe let's say 2, but we need to get it to 3. So again we get the distance and we multiply by 3 and we'll get a point around here. So this is our new lower joint, and now we need to get a now we can see that the distance between our new lower joint or our elbow joint and our hand joint have increased in distance. Now they may be around 5 between the lower and the hand. So again we get the direction between the hand and the lower, and then we multiply by 4 and we may only get around here. As you can see that it doesn't reach the target now, but it's more accurate than where we first started off, which was, let's say this is where we started off, and we've reached this much closer to our target. Okay, and this algorithm doesn't solve the inverse kinematics problem in one go. What it does is it repeats the problem, like let's say 20 times, and by 20 times it will be really close to the target. So it's a heuristic problem that never actually reaches the target, but you won't be able to notice the difference. It will be like 0.111, like 0.0001 off the actual target, but it will never fully reach the target. There will always be tiny inconsistencies. If you're looking for a perfect inverse kinematic solver, then this is not for you. For gaming purposes, this is perfect, okay? So we repeat this process over and over again, and by the end we will reach so close to this target you won't be able to tell the difference. And this will all be done in a very short amount of time. Okay, so this whole process will be done extremely quickly. Okay, so in around 20 frames, let's say. That's nothing. Okay, now we finished the forwards problem. Okay, and now we just need to update the positions. Alright, so now that we got the new joint positions, what we do is we set our little cubes to these new positions. And then in the next episode, what we'll do is we'll create a little mesh in Blender, and we'll rotate the mesh object, the armature on the arm in order to suit the positions of these joints. Okay, so quick recap of what we did. I'm just gonna rub everything out and just give you a quick recap. Okay, so we just have 3 joints. Okay, 1, 2, 3. Okay, let's just connect these up. Okay, now the distance between these joints, we get the initial distances 3 and 5. Okay, now we set a new position, so this is our target. Okay, and our little hand gets automatically moved from here, okay, all the way over here. And now our distance between the 2 joints is inconsistent. So what we do is we get the direction from the hand to the lower joint, okay, and then we multiply by our original distance to get a new lower joint point, which is now a distance of 5. And now the distance between the upper joint and the lower joint has changed. So we get a direction from the lower joint to the upper joint multiplied by 3, and we may get a root point over here. Okay, now our root point is not where it originally started, which is right there. So what we do is we reset our root point to the middle again. We see the distance inconsistency, so now we just get a direction from the upper to the lower multiplied by 3 because that was our original distance, and we'll get a new hand joint around there. Okay, and now we get the direction between the hand joint and the lower joint and multiply by 5, and it may be around, let's say, here. Okay, and that's how our FABRIK algorithm works. And now I'm going to explain how constraints and all of that work. So before we go into constraints, I would like to show you something called multiple end effectors, which is what we're going to be using to allow our character to lean over. Okay, so I'm just going to draw a little red dot here. Okay, that is going to represent our middle of our chest. Okay, and now I'm going to draw a left arm, upper joint, left arm, lower joint, left arm, arm joint. Okay, and then I'm going to draw a right arm, upper joint, right arm, lower joint, and right arm, hand joint. Okay, and now I'm going to add a new joint in called the pelvis, or the root of the root. Okay, so this is our root now. Okay, so since FABRIK is so powerful, we can modify the algorithm to suit any situation. And since we want a little leaning functionality, we have to be able to have another root for the root. So this is how our arm currently connects. Okay, I'm just gonna have this. Okay, so this is how our arms are. We can see the general arm position now. So what happens is now we have this joint. So what will happen with this is when, for example, we actually move the whole right arm, let's say right arm, even more towards this direction, right? Our current position cannot reach that because it's too far away. Our arm can only go up to this position. So what we will actually do is we will be able to modify our root position to be leaning slightly towards the right arm. And now what this will allow us to do is it will move all of the joints towards that position. Okay, so let me redraw all of this. So our root of the root will always stay consistent, so that's our little pelvis object over there. And let's say now that we are leaning towards the right arm, our right arm can actually be able to reach the position that it wants. So our right arm moves more in the right direction, and now it can reach the position that it wants. Okay, so what happens with the left arm? Now the left arm is also dragged along with the root because it is a child of the root. So we can see that the actual right arm stays consistent. Okay, so the right arm and the left arm will start to affect each other and essentially move the root around. So the way that the root position is calculated is that we do the backwards step of the inverse kinematics, and we get the new root position that we set. I showed you in the explanation before that the root has to be reset in the forwards stage of the inverse kinematics. So when we do the backwards step, we'll do the backwards step separately for each arm, okay? And once we do that, we'll get the average position of the new root, and then we will set that to the player. And what that will do is when the body is reaching more to the right, the root will find the average that the right is more powerful, and it will move more to the right. If the left is leaning, if you're reaching more towards the left, then the root will move towards the left. If you're reaching more towards the forward direction, the root will move forward. But there is one problem with this. In this example, the root can move as much as it wants, and that is not cool. Because if the root can move as much as it wants, then our arms can again stretch wherever it wants, and our body can't stretch. Right? So how can we counteract this problem and actually fix it? So imagine that this is the root, okay? And then we have the root of the root, which is the little pelvis object. Let me make it a nicer color. So the pelvis over here. So what we do is we are going to create something called a spherical constraint. So what this is in 2D it's just going to be a circle, but in 3D it will be a sphere, right? So you can move backwards, forwards, left and right. Okay, so what this is going to be is a little sphere that we're going to create, not visually, but we're going to create the sphere in code, okay? And what we're going to do is make sure that the root cannot leave the sphere. So once the actual root reaches this position, for example, right, it will get clamped to the edge of the sphere, so we'll never be able to leave the sphere. But what the real power of this sphere is that it's relative to the pelvis. Okay, so since the sphere is relative to the pelvis, whenever we move the pelvis, the actual root, the sphere moves, so that the root always has to stay consistent to the pelvis. Okay, so that the root can only move in the sphere, and then this parent object controls the sphere. And what we're going to do now is actually have the upper joints, okay, so these are the upper joints, and we're going to have constraints on them as well, because we don't want the upper joints to move as much as they want either. Okay, so if you move your arm around, you can see that your upper joint has limits, right? So we're going to set a sphere around there. But the thing with this new constraint is that it's relative to our root. Okay, so these two spheres are relative to the root, and that's how we're going to achieve constraints in our actual algorithm. Because in the actual FABRIK algorithm, instead of relative spheres, it's actually like relative cones. So it will have a cone going in this direction, right? And then you can only move, the upper joint can only move inside the relative position of that cone, which is more effective, but it's a lot more complicated to create, and I don't want to go into that right now, mostly because I don't understand it fully, and if I can't understand it, I can't teach you guys extremely effectively. Okay, So what we're going to do is have spheres that are relative to the parent object, so that the objects are always constrained unless the actual parent moves. Okay, so that's a little addition that I made. Okay, so one other problem that we're going to be tackling throughout this whole series, sorry, not series, it's like a mini series inside a series, is that what happens with arms and three bone joints is, normally what happens is, so let me just draw some joints over here. So that's our little lower joint. This is our little hand joint. Please make that mistake. Here we go. And the upper joint. Okay, so let's say that the target is now moved to this position. Okay, it's actually directly in front of this lower joint. Okay, and it's in line with all of these other joints. Well, we would have to move the hand joint over here and bend it, right? But which way do we bend the arm? Would the new arm be bent like this, or would the new arm be bent like this? How would our computer know? So what happens in these situations is that it will create a really jittery motion, or most likely it will land on an unnatural position. When you bend your arm, it doesn't bend inwards towards your, like if you try bend, your arm doesn't bend like inwards, right? So we need to make a new object that actually defines which way our arm needs to bend. So what we're going to do is, if we want our arm to actually bend it in this way, we're going to have something called an elbow effector. So there's going to be a little cube across here, right? That is going to essentially tug on this lower joint at all times, alright? So whenever the backward step is conducted on the IK, the lower joint will be moved towards the elbow effector, or the bending effect, or whatever you want to call it, by just a certain amount that you can define. So I'm going to give a range between 0 and 1, which the anyone can pick, and the higher this number is, the closer or the more your arm bends towards the elbow. Okay, it doesn't even matter if the number is 0.001, it will still bend towards this elbow. So whenever our IK is in a situation like this, which it is a lot of the time, trust me, our arm will bend like this because it has a little tug in this direction. Okay, that's another little modification that I have made to this algorithm to make it more powerful. So it always bends in the natural direction that you set it, and this has extreme power because you can move the elbow in runtime. Right? So if you can move the elbow joint effector in runtime, you can essentially move which way your elbow is facing. So that also has extreme power. Do you want your arm to be facing down? Do you want your arm to be facing outward? Whatever you want. This can create a lot of movement, and has heaps of freedom in what you want to do with it. Okay, so this is just a basic introduction to FABRIK, of how whatever we're going to be implementing for the next 3 episodes, and I'm sure that after that we will be implementing full body IK with forwards and backwards reaching inverse kinematics, and I would have learned how to do proper constraints by then. But for now, this is really realistic, and it's probably better than any other IK you've probably seen on YouTube. Okay, once we get the full body IK in, our game will be amazing. So let me actually get into the tutorial of how to code it now. So today's episode is going to be really long. I apologize about that, and let's get into the tutorial. Okay, I hope you had a good introduction to FABRIK, and if you didn't and you need more information on how this algorithm works, I've left one link in the description which has a YouTube video showing you exactly how the FABRIK algorithm works, forwards and backwards, and then I also left a paper in the description which you can download and read for yourself, which has all the details of FABRIK algorithm, including constraints and multiple effectors. Okay, so I'm going to begin coding the algorithm. So how we're going to be doing this is actually through some temporary cubes that we're going to be having inside the capsule, which is going to be where our algorithm is going to be implemented. So we're going to visualize these cubes as joints. Okay, so these cubes are going to be our joints, and we're going to implement the algorithm onto these joints. And then once the algorithm is implemented, then we are going to wrap our player arm mesh onto these joints to fit the exact positions using some simple math, and it will look very nice, precise, and it will have very nice precision as well. So what we're going to do now is create a little cube. We're going to scale this down and remove the box collider, so we're just going to remove that fully. And we're just going to go into isometric view and drag this cube into a capsule. Okay, and we're going to center it out. We're going to call this cube the centroid. This series, it will last around 2 to 3 episodes. The first episode we will just be coding the beginning part of the algorithm. In the next episode we'll be constraining the arms and creating some root movement, so some multiple end effectors and all of that extra algorithm stuff into the code. Okay, so the first part today will just be implementing the algorithm. Okay, so it won't be super complicated, but I promise you it will be amazing. Okay, so we're gonna create the centroid, and we're just gonna set this at 0.5, so it's a bit higher where the middle of the arms would usually be. Okay, and then we're gonna duplicate, drag it out here, and let's set the X to we're just gonna drag this new cube object underneath the centroid, and let's call this upper right. Duplicate that one, call this upper left. Okay, so upper left will, let me just set all the z values to this, and upper left will be 5 and the upper right will be x -5, and make sure the z and y values are 0, so we have a 0 y offset and 0 z offset to the centroid. Okay, now we're going to create a lower right and lower left, and you just parent these two new bones onto the upper right and upper left, and let's just name these lower right and the lower left. Okay, lower right, we're going to set this to -5 on the x, which is going to be our offset, and lower left will be just a 5. I don't know, why I called it left and right is left from the actual view of the player. Oh no, looks like I inverted it, so this should be actually a left and this should be right. So let's just go ahead and change that. Upper left, you might have had the right mind to do it correctly, so lower left, upper right, lower right. Easy stuff. We're going to duplicate lower right, we're going to duplicate lower left, and we're going to make these two new objects a child of the lower objects. So we're going to call this hand left and hand right. Okay, hand right will be an offset of 5 from the x, and hand left will be a offset of -5. Very easy, basic stuff. So these are going to be our joints. Okay, so this is an upper arm joint which is connected to the root object, and this is our upper arm, lower arm, and each one will be modified separately to create our IK. So what I'm going to go and do right now is just go into our centroid and just create, just click on that game object icon and change this to green so we can always see where the centroid is at. Okay, now we are going to create just 4 more joints. Okay, so we're going to duplicate the hand right, drag it out, and we are going to call this the right effector. So the effector, like I explained in my video, is just where our right hand is going to be looking. Targeting, actually, should be the correct term. And our left effector will be where our left arm is targeting. Okay, so we have these 2 effectors, and now we also need 2 more joints. These are actually not joints, these are elbow bones, kind of elbow targets, kind of is what they are. So basically what these elbow targets are is basically we want our arm to always bend in a natural direction, okay? So in order for it to bend in a natural direction, we need to have a target showing the actual character where the natural direction is. So we will have this elbow effector, you can call it whatever you want, just another effector that this bone right here will be linked to, so it'll always be dragged slightly towards this, so we'll always have a natural V shape, always facing in the direction of the elbow effector, okay? So it will just give us some more extra control on where we want our elbows to be pointing towards, okay? So it's very nice little touch that we want to add. Always want to add that, especially on arms and legs, so we can get proper control. So I'm going to call this right elbow and just set this onto the right effector. And then I'm going to duplicate the right elbow, call this left elbow, okay, and I'm going to drag this onto the left effector and just set the X to 0 and this to -0, and then we're just going to drag this until it's around the center of the elbow. It doesn't really have to be exact, I would just like it to be quite precise. Okay, alright, now we have all of the bones and everything that we need. Next episode we will add a pelvis object, but we don't need that for now at all. Okay, so let's simply create an object here to display where the right elbow is, and a object here to display where the left elbow is. Here we will add we'll just change the name here to RE to show that this is the right effector, and we'll say LE here to show that this is the left effector. Now we will get right into the coding. Okay, so to begin coding, we have to create our object. So I'm going to create two scripts, just actually one script, and we're going to apply it to two objects. So I'm going to create a script called armIK. Okay, so I'm going to save this, and let's go back into Unity and go into our assets, and in our scripts I'm going to create a new folder called IK. And I'm going to go into our assets and drag our armIK into our IK folder. So I'm going to go into our right effector and make sure armIK is attached to that. Go into our left effector and just attach our armIK onto that one. Okay, now let's go into armIK and begin coding. Okay. Oh, where is armIK? Let's open it up. There we go. Okay, I hope you guys can see that. I realized on my last video that the font was a bit smaller. And just one more thing. One of our commenters suggested that we implement more things into our behavior editor that we did start in episode 2, and I certainly will be doing that with the FOV pathfinding and shooting very soon, but I just want to finish IK first and then I'll go straight into that. Okay, so let's begin our coding. As usual, you guys know that I like to region out my code, so we're going to create a new region called variables. And you also know that I would love to declare all the variables that we need for this episode before we actually begin coding. So let's create a little header to keep things nice and neat and call this options. And we're going to add a public float called elbow power. So let me just explain to you what this is. I'm going to add it from a range of 0 to 2. Okay, so elbow power, you see this elbow? This is basically how much the bones bend towards the elbow. So we'll find a normalized distance, direction, between this joint over here and the elbow, and then we'll multiply that by the elbow power and push the joints towards that direction by that much amount, okay? So we don't want any more than that, any more than 2, or it will just look unrealistic. Even 2 is a bit much. We don't need that. 1 would be the most, but I'm just giving some extra care if you guys want to change it up. I don't know. Now we're going to create a header called joint references, and we're going to basically pass in everything. Okay, public transform end effector, public transform centroid, public transform upper ref, public transform lower ref. So all the refs are basically our cubes, which is our joints. Okay, once we get into actually wrapping the mesh around the joints, then we'll have different variables for that. Okay, but we're not gonna get into that right now. And then we're just going to declare all of our private variables. Okay, now the private variables, just one of them needs to be public. So we're going to create a hidden inspector because we don't need to show this. We're going to call this centroid position. This is public because later when we use multiple end effectors, the movement of the left arm will affect the centroid, which then will affect the left arm. Okay, so the right arm will affect the left arm will affect the right arm, the elbow of the right will affect the left arm. Everything affects each other. That's why FABRIK is so awesome. You can make it affect each other, right? And you can have full body IK with everything interacting with everything. Okay, and many other IK solvers which just find the angle, which I've seen a lot on YouTube, won't be very dynamic. It won't look natural is the main problem with most of the other algorithms. Okay. And many other IK algorithms are very complicated as well. So we're going to create another vector3, temp centroid, private vector3 temp upper. So what we're going to do is we're going to create a temporary variable for every joint. So this is the variable that we will be applying our algorithm onto, and then we'll modify the joint positions at the end. Okay, now we're going to have some distance variables as well. So we're going to have a public float called centroid to upper dist, private float upper to lower dist, and private float lower to hand dist. Okay, so these floats basically are the distances between our original joint positions. And this is important because IK needs to always maintain the distances between the joints. Okay, that's one of the most important aspects of IK. We can't modify the actual distances between the length of the joints, okay? When you extend your arms don't stretch in order to go where you want it to. Your bones actually bend in a way that you can reach over and grab something. Okay, so that's how we're gonna build this. And yes, if we do pull our arms, our effectors too far, our body will actually, our centroid will lean towards the target and help the IK reach the target more effectively. It's actually pretty awesome once we get to that stage in the next episode. And don't worry, I will be uploading very quickly the next episode because I have everything set out. This video just took a while because I wanted this video to be fully featured. Grant Christie actually suggested me to make this more complicated. I was originally going to do a very simple version of FABRIK, but now I'm doing a more complex, more dynamic way of FABRIK. So you can thank Grant Christie in the description if this helped you out. Okay, so we're just going to check if the hand ref is no, and just as because this is the last variable you would probably assign, so if that's not no, then all of the other variables should be assigned. We're just assuming, doesn't really matter. And we're going to draw our gizmo, make everything look pretty, visualize the joints and all of the connections. So we're going to change the color first up to cyan. Alright. And then, okay, alright, I need to learn how to type. I'm going to gizmo.drawLine from our upper ref.position to our centroid ref. Oh, I don't have ref here. Centroid ref. Not red. Ref. Centroid ref. Dot position. Okay, so we're going to draw a line from our upper position to our centroid position. Now we're going to change the color again to gizmo.color equals color.yellow, and we will draw a line from the upper ref.position to lower ref.position. So normally this algorithm will be applied with an array of bones that you just pass in, and the algorithm calculates all of the distances, everything, and just goes through a for loop and just modifies all the bones like that. But we're going to be doing it step by step so you guys understand it, and when we get to full body IK, then we will do it using loops, okay? So we're gonna draw another line from Gizmo. Draw line from lower ref dot position to hand ref dot position. So I'm just showing you guys the connections. Okay, now so Gizmo dot color equals color dot magenta. Okay, and we're gonna draw a line from our lower ref dot position to our elbow ref dot position. Yeah, I'm just connecting everything up, and I forgot to create an elbow reference. Okay, forgetting heaps of stuff today, but we should be good. Gizmo.color equals color.red, and now we are going to draw a small little sphere around the end effector, which is going to be a radius of 0.1 f. Okay, now if we go back into Unity and just check out what's going on, let's just go in and assign all of our variables. Let's go into the right effector and add in all of our stuff. So centroid is this object over here. Right elbow, oh no, that's not the right elbow. This is the right elbow over here. Upper ref is the upper right. The lower ref is the lower right. Hand ref is the hand right, and boom. We should have a connection between the hand ref and the target, just because it will look nice. So let's pick another color to represent that. Let's make it green. Gizmo.draw line between hand ref dot position and end effector dot position. Okay, let's go back into Unity and check that out. Okay, looks nice, looks nice. So we have a nice visualization of what's going on, and we will be able to see the joints actually bending. So this is what I meant by the lower arm bending. The arm will bend like this. As you can see, it will always face towards the right elbow. Okay, let's undo that and go into our left effector and just configure this. So the end effector is LE, left elbow is over here, our centroid reference is over here, upper reference is the upper left, lower reference is the lower left, hand reference is the hand left. Boom. Okay, now we have two arms. They are a bit long. Actually, no, they're not. I'm just looking at the green as well. No, that's perfect. Perfect. And let's begin coding our actual algorithm. I love visualizations, but they take up so much time. Okay, now we are going to have a private void awake because we need to set up our variables. So what variables do we need set up? We need to set up our distances and our original positions. Okay, so let's just do that. Private void setup variables. Just have a quick void over there. Set up variables. Let's call this in the awake method, and let's begin. Centroid to upper dist is vector3 dot distance between the upper reference dot position and the centroid ref dot position. And let me just explain. Centroid to upper dist is basically this blue line between one arm. So the upper arm to this centroid is the centroid to the upper dist, and upper to lower dist would be this one, lower to upper dist, hand to lower dist would be this one. Okay, we're just going to calculate those in the awake because we don't want to calculate them every frame, or they would be changing every frame, and we do not want that at all. Upper to lower dist, here we go, vector3 dot distance, upper ref dot position, lower ref dot position. Boom. Okay, upper to lower dist done. Lower to hand dist equals vector3 dot distance between our lower ref dot position, hand ref dot position. And now we're just going to set up two variables. Centroid position, centroid pos equals centroid ref dot position, and temp centroid is equal to centroid pos. Okay, easy stuff. Now we've set up our variables, and I'm going to create a new region called setup over here and end the region over here. Just for this video, we are going to be running the IK algorithm through this script in itself, but in the next video we'll transfer the running of this script to a main script which will get all the arms and then get the average position and do a bunch of calculations like that. So that will be very fun, so make sure you stay tuned. And in order to stay tuned to this series, just make sure you subscribe and just watch the rest of the series. It will be pretty amazing, I promise you, and you'll learn stuff that you never learned before. So I'm just going to create a region called algorithm and end region. And if you haven't learned stuff like A star and all of those pathfinding algorithms, everything's coming. Everything I've learned I want to share to you guys. Okay, we're going to create a late update. The reason we're doing late update is because the animation controller, or all of the animations that you create, will use the update function. And as soon as we finish the update function, the late update function is called, and we can apply IK to our late update function, so our IK works side by side with animations without overriding the actual animations or causing some weird effects. Okay, so we're just going to create a late update there, and we're going to create a public vector3 called solve backwards, and this is actually a function that will return a vector3. So what this function will do is it will move. So as I explained in my video, we will start at the hand. Okay, we're going to start at the hand, move the hand to the right effector, and we're going to calculate the distance between the hand and the lower disc, move the lower arm, then we're going to move the upper arm based on the lower arm, and then we'll move the centroid based on the upper arm. Okay, so that's the backwards solving part. Okay, and when we do the backward solve, we can calculate the new centroid position, and we are going to calculate that, and we're going to send that off to another script in our next episode. So we won't be using it right now, but once we calculate the new centroid position of this arm and this arm, then we'll find an average of those centroid positions and stick it right in the middle. That's why we are returning a vector3. So if you watch my video, you'll understand what we're going to do in the solve backwards part. Okay, we're going to create another void called solve forward as well now. Okay, so these are our two main methods. And one more main method actually that we need is set temp pos. Okay, and this will set all of our temporary positions. And I'm just going to go ahead and do that now. We're going to set the upper ref.position to temp upper, and we're going to set the lower ref.position to temp lower. We're going to set the hand ref.position to hand lower, temp hand. Okay, and that should be fine for now. We will change that later, and let's just set centroid pos equal to centroid ref.position. Okay, and we won't be moving the centroid ref just yet because the root position always stays the same unless we're doing multiple end effectors, which we're not doing for now. Okay, in late update, we need two parameters, sorry. For our solve backward, we need one parameter, which will be vector3 end effector. And then here we need to pass in a vector3 root point. Okay, so the reason we're doing publics and all of these parameters and stuff is because another script will be controlling this in the next episode, so just getting everything prepared for that. Okay, now we're gonna go here and go return temp centroid. Okay, we're just gonna add that now, and in late update we're gonna go ahead and add solve backward, because always backward then forward, and then we're going to set the positions every late update. Okay, so we're going to solve backward from the end effector.position. Okay, so the end effector is basically just this cube over here. This is where we are trying to go. Okay, in the documentation of the FABRIK or in the YouTube video that you watch, they will tell you to check if the distance is greater than the maximum reaching distance, and then change all of the joint positions and stuff like that. But we're not going to do that because the algorithm has the capability to do that itself. It will just have a bit more processing time, but that's not very important for us. What is important for us is quality, and we're going to get that. So solve backwards, we're going to first set the temp centroid is equal to centroid position. Okay, we're just going to set that before we even start. We just need to make sure we have that in check. And now we will start the actual thing. So as I explained in my beginning intro video, the temp hand first will be set to the end effector. So the hand will be set to the end effector. And then we find a direction between the hand and the lower. So let's call that hand to lower and go lower ref dot position minus the temp hand dot normalize times lower to hand distance. So let me explain what this is doing basically in Unity. Okay, so first we get a distance between the lower ref and the hand ref. Okay, so what happens then is when I move this hand ref over here, for example, no, I will actually be moving it over here, we can see that the distance is way too long. But how do we keep the distance while maintaining the direction? So what we do is we get a direction between this hand and this lower, right? And we normalize that. And we normalize that, we get a value of 0 to 1 in each x, y, and z variables of the vector. Okay, and then we multiply that by our original distance of our hand, which is around here, right? And when we do that, we get a point with the same direction but the same distance as what we started with. So if our actual position that we set it to here, right? We multiply by our original distance and keep the direction, it will be moved to around here and it will preserve the distance, okay? So that is the basic idea of this whole algorithm. That is how we will be doing the whole algorithm forwards and backwards, and in the end with constraints. That's how we will do the whole thing. Okay, so that's the basic idea. I hope you understood that. I tried to explain that to the best of my ability. So what we're doing here is finding a direction between lower and the temp hand. We're normalizing that, like I said, and we're multiplying that by a lower to hand distance. Now we're going to set our temp lower, which is our lower joint, to our temp hand plus hand to lower. Okay, because we found a direction from the temp hand to the lower ref. Whenever you minus a vector from another vector, the second vector, or the B vector, which will be the origin, and this will be the target, okay? So we plus hand to lower by the temp hand, which will give us a direction towards the temp lower from the temp hand. So we have to add the temp hand, okay? And we're also going to add one more thing, just for the temp lower variable. Elbow ref dot position, like I said, target first, lower ref dot position, origin second, elbow powers. So like I said, we're going to normalize this actually. And like I said, we're going to move the lower joint towards the hand to preserve distance, and then we're going to move it slightly towards the right elbow based on our power. Okay, so we find the direction between the elbow and the lower and move it towards the elbow. So this whole thing is for repositioning the lower joint, which is this middle one here. Okay, because our hand joint has already been repositioned to the target. And in our next iteration, which is the forward solve, we will move the hand back to only be able to reach as far as the maximum distance. Okay, so I hope I'm making myself clear. If I need to improve my teaching or explaining skills, just leave it down below in the comments and I will try my best just to explain what I need to improve, and I will certainly improve that. Now that we have repositioned the lower joint, we want to reposition the upper joint to preserve distance from the lower joint. So let's imagine that we move both the upper and lower and we have preserved the distance. So this is what it would look like in the first iteration. But we won't actually see this when we're playing the game. Now the distance between the lower and the upper is way too big. So now we have to find the distance, do the same process, keep the direction, multiply by the original distance, and then we will move the upper to fit the position where the distance is the same. And then we gotta do the same to the centroid as well. Okay, so it's basically a repetition of the last step, but with different joints. Okay, so let's call this lower to upper is equal to upper ref, remember, target first, position minus temp lower, okay, because we moved the temp, and dot normalize times upper to lower distance. Okay, now temp upper is equal to temp lower because we are going from temp lower in the direction of upper ref. Temp lower plus lower to upper. Okay, we don't need to add the elbow stuff in this part, because the only thing we're going to be adding elbow to is the lower joint. Okay, easy thing there. Okay, vector 3, now we got to reposition the centroid to be the same distance from the upper. Okay, vector 3 upper to centroid is equal to centroid ref dot position minus temp upper dot normalize times centroid to upper disc. So we're basically calculating the same thing again, and we're just making sure all the joints preserve their distance. Okay, so that's the main goal. And see how we move the temp head to the end effector. That will basically be the how we solve the IK. It's actually a very simple way of solving IK, but it is so powerful when you use it in the right way. Upper to centroid. Now I've realized I haven't finished all my iteration code over here, so let's fix that. Solve forward, and we'll be solving forward from our temporary centroid position. Okay, now set temp positions, and I'm just gonna make sure that we're not resetting temporary centroid positions. Just gonna make sure here. Okay, everything's fine. Okay, now we're gonna go in and we're going to update our solve forward part of the algorithm. Now we're gonna do exactly what we did. So let's imagine. Okay, move all of these guys over here. Okay, let's just imagine our centroid is over here, but our original root point, like I explained in my video, is over here. So now we got to move the centroid all the way back, like we snapped the hand to the end effector, right? We're going to snap the centroid back to its original root position, and then we will make sure that the upper arm preserves distance to the centroid. Then we're going to go through and make sure the lower arm preserves distance to the upper arm, and then the hand joint preserves distance to the lower joint. Okay, so then everything will be perfect. So I'm going to go in now, and I'm just going to go in and begin coding our solve forward. So temp centroid is equal to our root point, so basically what we're passing in. Now, vector 3, centroid to upper. So we're setting the temp centroid to the root point, and we're passing the root point as the temp centroid. Okay, so the temp centroid, every solve backward frame, will be set to the centroid position, which is the original upper reference position. Okay, and here we set the centroid position to the centroid reference position to make sure when our player actually moves, the centroid is updated so that the root isn't stuck over here, and our IK keeps snapping back to this position. It stays relative to our player at all times. So centroid to upper is equal to temp upper, losing my voice right now, temp upper minus temp centroid dot normalize times centroid to upper distance. Okay, temp upper is equal to temp centroid times, sorry, not times, what am I doing? Plus centroid to upper. Okay, so finding the direction between the centroid and the temp upper, normalizing, multiplying by the original distance, resetting the temp upper. So we're going backwards now. Okay, well, I mean backwards, I mean forwards. Okay, forwards from the root to the end, and backwards is solving from the end to the root. Okay, vector 3, upper to lower. Temp lower minus temp upper dot normalized times upper to lower distance. Okay, now we go temp lower equals temp upper plus upper to lower. Okay, vector 3 lower to hand is equal to temp hand minus temp lower. I think you might see the pattern here now. We're going from the lower object in the hierarchy to the upper object. So lower to higher, lower to higher. And then here we went from a higher to lower, oh god, higher to lower, higher to lower. Okay, so that's just a little pattern for you guys to remember this off by heart, because once you learn this, you can implement this in so many different ways. It's actually crazy. Once I learned this, I just saw so many possibilities in my own game on how to implement this. So Let me just capitalize this. Okay, look at this. Alright, now we have the basic algorithm. This should technically work. If it doesn't, I may have some idea. Okay, let's go back. And we have basically finished our algorithm. So let's play this. Let's check that we are on track. And as you can see, we are certainly not on track. And I think this is because of our centroid being set to our temp centroid instead of our actual centroid. So let's just change this from temp centroid to centroid position and try that instead. And if it's not, I'll have to pause it and check it out, but it looks like it's working. So let's play this game, and it looks like we created the whole thing in a reverse direction. So let's just instead of being in global, let's click on local up here, and it will change it to local space. What we're gonna do is get the centroid and rotate this whole thing. So we're gonna rotate everything. Alright, we're just gonna rotate in this direction. We're gonna turn off pivot and go to center so we can rotate the whole thing. Okay, so we're gonna rotate the whole Y by around 90 degrees. So move it around here, and we're going to drag the centroid back into the center. So let's go back into our centroid, make sure that's 0.50. Okay. Now, once we're in the center, we can know for sure that all of our joints are centered. The rotation doesn't really matter because we're rotating the bones anyways. Okay, now let's play this, and we can see that we're facing the right way. Let's just try moving. We can see that our joints are moving, and we have a bit of delay, but that's fine. Now let's try our main part of the algorithm. Let's go into upper. Let's grab the left. Get out of center, go to pivot, and we can see that our elbows are in the wrong direction because we want our arms to bend backwards. So let's just drag those and bring them into the back, and let's get the left effector and bend it, and let's see what's happening. Alright, yes, okay. The elbows do have to be on that direction. No, the problem that we are having right now is I forgot to increase elbow power. So let's just set this to 0.05. Very, very slight increase actually. We don't want too much. So let's just try this. And go in and begin trying to solve our IK. So let's get our left effector, move this towards it. And as you can see, our arms are bending in a very natural position. And as you can see, our upper arm is coming out to the back, and it looks very unnatural at the moment, and we can have 360 degrees. So that's what our next episode is for, where we'll have very simple constraints. It's actually very simple, and I should have the video up in a maximum of 3 days, and it should be up very quickly, and I'll explain how to fix that upper joint rotation and how to wrap a mesh around it. But so far we can see that we have nice elbow control, so I can move the elbow, and you can see that we can focus our elbow in the direction that we want it to be focused. Okay, and then in the next episode we will get rid of some of that lag that you can see. You can see that it's just, if we move it, it interpolates very slowly, even though we have no interpolation method, and we can fix that quite easily, and we'll wrap the meshes around. We'll fix the constraining issue. We'll start moving the centroid to make more dynamic movement, and we have so much planned for the next episode. And the episode after that, we will be implementing aiming IK, so we can get these targets, snap them onto a gun, and we'll be able to move the gun, and the arms will be able to retarget onto the gun. Okay, and that should be it for this episode. I really hope you guys enjoyed. I know it's been a long time since I uploaded with all my school stuff going on, but I hope you enjoyed, and if you did, please leave a like, and make sure you subscribe to keep up with this content so you can add more features onto our IK. So make sure to subscribe for the original content, and I'll see you guys next time.